So the integral that I want to solve now is this integral minus infinity to infinity x to the n e to the minus ax squared minus bx minus c dx. And this is similar to what we had in the previous video, but generalized in two ways. First, our exponential is now no longer just e to the minus ax squared, but now we're no longer centering it at 0, we're centering it around some different point dependent on this b. And also we're extending this x here to be a monomial with both even and odd degree. And we're able to look at odd degree now because previously we had an odd function times an even function both centered at the origin, and so those would always go to 0. But now this is no longer centered at the origin, this Gaussian. And so because of that, odd monomials and even monomials will both have some non-zero, will both result in non-zero integrals. So that's great. How do we want to solve this integral? Well, we want to use the same type of trick that we used in the previous video. And in the previous video, we solved our integral using differentiation under the integral sign. And we want to do something similar to that here. And so the way that I'm going to do it is by taking n derivatives with respect to b of our Gaussian. And you might ask, well, I mean, so depending on which value of n you pick, there's a couple different ways you could do this in principle, right? I mean, if this was x squared, for example, there's two things you could do. You could either take one derivative with respect to a or two derivatives with respect to b. Both would get you an x squared out in front. Likewise, if you want to do, x to the 9, then you could take 4 a derivatives and 1 b derivative, or just 9 derivatives with respect to b. So there's not a unique way of doing this. But it's the most simple and easiest way just to take derivatives with respect to b, because then you don't have to worry about mixing derivatives for odd a or anything like that. But I would encourage you, try this out for one derivative with respect to a, two with respect to b, and make sure that you get the same answer. But I'm going to do it with respect to b because that's easiest. You only need one derivative for every single case. And so what happens now? Well, we can rewrite this using our Leibniz integral rule. And this becomes derivative outside of the integral with, to the n. And then the integral that we already know how to solve from the second video in this series. E to the minus ax squared minus bx minus c dx. And we know that this integral right here, we solved that a long time ago. And we saw that this whole thing right here was square root pi over a times e to the minus c minus, or rather plus b squared over 4a. And so if we can take the derivative of this n times, then we've got it. Then we have a solution. And I'll start by pulling a couple things out, right? So the only place that b shows up is right here, and so that means that we can rewrite this whole thing as minus 1 to the n root pi over a e to the minus c, and then the hard part, n derivatives with respect to b of this guy right here. Okay, great. So what do we do? I mean, really, we want a closed form formula for this because no one wants to take 100 derivatives of this exponential function or however many derivatives you need to take. So getting a closed form of this guy would be really nice. So how do we do it? Well, hopefully you saw my Hermite Polynomial video. Otherwise, check that out, link in the description. Because this is exactly what we would get from a Hermite polynomial. So I'll remind you that a Hermite polynomial in the physicist convention, or I think the simple convention, is defined like this. The nth Hermite polynomial as a function of x is what? It's minus 1 to the n e to the x squared times d to the n dx to the n e to the minus x squared. And so we can see right here that this derivative times the Gaussian is exactly the type of thing that we want to be able to plug in here. And so if we can get this in the right form and then solve for this in terms of everything else, then we've got it. Then we've got a nice closed form solution for this funny derivative term right here. So how are we going to do it? How are we going to go from this guy to this guy over here? Well, we can use a change of variables, right? And here, let's think about what that change of variables should be. So we know that the argument of this exponential right here should be b squared over 4a, and right now it's minus x squared. And so what that suggests is that what we want is x being set equal to b over 2 root a. That'll get all these terms, right? But we have an extra minus sign here. But in order to fix that minus sign, in order to make this go from positive or from negative to positive, we have to introduce an I. And then when we square that, it'll cancel out and we'll just get positive b squared over 4a. Okay, great. And so this is the change of variables that we want to use, db. So let's plug this in and see what we get. So we're going to get hn of x, or rather, I mean, in this case now it's hn of ib over 2 root a equal to what? Equal to minus 1 to the n e to the minus b squared over 4a, just squaring this x here. And then what? Well, we're going to have d dx, which now, we want to rewrite in terms of b. So what are we going to get? We're going to get 2 root a over I to the n, dn db to the n. And then exactly what we want, e to the b squared over 4a. Perfect. Okay. Now what do? We just solve for this guy. So we divide all these terms over here, plug it in here, and then we're done. We've got it. And so let's do that. So this whole integral right here, we can write as minus 1 to the n root pi over a e to the minus c, and then solve for this guy, which is going to give us what? hn of ib over 2 root a over minus 1 to the n. We're going to have an e to the b squared over 4a from dividing this over, and then we're going to have this guy right here, which is going to give us I over 2 root a to the n. Okay, we've done it. The only last thing that we might want to do is simplify this a little bit, and so we can do that. And what's going to happen? We know that this is going to go away. We can combine the exponentials, and what we're going to be left with is this. Root pi over a, I over 2 root a to the n, and then e to the b squared over 4a minus c times our Hermite polynomial, hn ib over 2 root a. And so we've done it. It took a little bit of extra work because we had to introduce these Hermite polynomials, but we were able to take this very general integral up here and using our Leibniz integral rule or the differentiating under the integral sign trick, turned it into a very nice, a relatively nice closed form solution, all in terms of the stuff we know. So I think I'll stop there, and I hope to see you in the next video.